Part which we are going to dive deeper into is the model serving or model inferencing, right? And I believe for the most part, the end goal of the machine learning lifecycle, right? Ultimately, all the activities which we are doing, and not even the machine learning lifecycle, I would say, even when you look at all the efforts you are putting on the data part of the lifecycle, which is cleaning your data, ingesting data, transforming data. Ultimately, the resulting model which is deployed in production is essentially what has brought that intelligence where it has learned over that data, and now it's ready to perform in a real world with real world data and give you the results, right? So that becomes in a lot of cases, right, the most important thing which you would do, right? Putting your machine learning models in production. And I think this is one of the slides Chibik talked about yesterday, why something like this can be so hard, right? Uh, until this phase, you are mostly in experimental phase where, if you do have errors, if you do have issues, right, they probably can be resolved. But once it is live, it is live. And when the models are running in production, right, you definitely have to account for the capacity usage. I mean, these are not things which you can run on 0.5 vCPU, CPUs, and even if they are running long time without handling any customer workload, they are fine. You're more probably running it on expensive GPUs, etc., right? And you want to make sure that when there is no incoming usage for that particular model, right, it's not hogging those resources, right? You want to be able to continuously monitor the health of those models, right? The other part is, right, is the rollout safe? How do I roll back? So because you're producing new versions of the model on a more consistent basis, you will be rolling out new versions of the model on a new consistent basis. And when you are doing that, you want capabilities for A/B testing, pin rollouts, canary rollouts, which need to be integrated as part of the model serving platform, right? The models, when deployed, they need to be able to serve multiple kinds of protocols: HTTP, gRPC, incoming streaming requests from Kafka. You probably want capabilities for batch prediction. You essentially also are looking at a way so that your data plane protocol, so once your models are deployed, you're not changing because, hey, I now need to move my model from Azure to AWS, or I'm running an open source platform like KF Serving or Selden, and I'm moving models between them, but now I have to rewrite my clients because I was using the data plane protocol from one versus the other. Right. And last but not the least, the thing which becomes also very important is, the advanced metrics, quality metrics, as we call it, around models, right? So whether there are drifts, anomalies, are the models, vulnerable to adversarial attacks? Are they giving biased predictions? Right. All these things come into picture. Now, this is a problem which was being solved in multiple stages by different providers, right? Our focus, at least from an open source perspective, was on the serverless machine learning, right? So somebody asked, right, what does serverless mean in this context? So essentially the idea, as I mentioned, that if you're not getting any traffic, you should not be consuming the resource, right? You should not be consuming memory. You should not be consuming GPUs. The model should, slide back into oblivion until and unless it needs to serve the traffic again, right? So that's essentially, the concept behind serverless. When your apps are not handling any incoming user requests, they should not be consuming any resources, right? Plain and simple, right? So that's where, we were focused a bit. Tommy and I gave a talk at the KubeCon in 2018 around that, leveraging Knative under the covers. The co-founder of KF Serving LLC was in that talk as well. We met, and then we started springing up this idea around KF Serving. Definitely, Selden has been doing a great job around graph inferencing. So multi-model graphs. They had capabilities, to actually provide drift detection, anomaly detection, analysis. Google has been focusing a lot of efforts around TF Serving for TensorFlow, given the ecosystem they are most passionate about. And at Microsoft end, right, the Azure machine learning stack was totally getting onboarded on top of Kubernetes, right? So they needed similar capabilities, right? So it was the right time for all these companies to come together and start standardizing towards one machine learning inferencing stack. And that's when the genesis of KF serving happened. Bloomberg was also investigating the serverless characteristics. So that formed the basis of KF serving, and Kubeflow provided that incubation environment which you need for multiple vendors coming together and standardizing and building one platform. So yes, we co-founded that and under the Kubeflow community. And our initial focus had been around 80% of the use cases, single model rollout and update, with the key characteristics that we want serverless machine learning inference, we want canary rollouts. At a minimum, we wanted to provide model explanations, and definitely if you have need for pluggable pre-processes and post-processes, that should be a capability, right, which is available as part of this machine learning platform. So this is the stack for KF serving. Definitely, as with everything in Kubeflow, running on top of Kubernetes, but also, bringing in Istio and Knative for different reasons, and I'll talk about those, right? And then on top of, all the machine learning specific capabilities, right? To be able to handle multiple frameworks for different kinds of machine learning and deep learning models, to be able to provide pluggable capabilities around pre-processes, post-processes, explainability, and moving forward, threat detection, etc. Now, why we chose Knative, right? So essentially, as I mentioned, right, Knative is a project, which originated around the Kubernetes ecosystem with a focus on serverless machine learning inferencing, right? The core idea was that, you wanted to scale to zero and you wanted to auto scale from zero upwards, right, based on incoming requests. Now, this is a community, right, which is very strong. IBM is the second largest contributor there. Red Hat, Google, IBM, and many others, VMware, right? They're contributing heavily to Knative. Just recently, IBM also announced, multi-tenant Knative as a service offering on IBM Cloud. The Knative managed Knative installs on Kubernetes clusters has already been available since last year on IBM Cloud, right? So strategic investment from IBM, strong focus, and it made a lot of sense, right, for us to be basing and using this from a serverless capability perspective. Now, Istio, on the other hand, right, provides a lot of capabilities around traffic control and load balancing and resiliency, right? So the idea behind Istio was, as the proliferation of microservices happened and everybody started, taking their monoliths, making, microservices out of it, there were some functions which were common. What was happening was, those common functions were being rewritten for every single microservice, right? So you need ingress load balancing, you need traffic routing, you need authentication authorization, you need, encryption of your service to service communication, you need policy enforcements. Now, all these services are common, but every microservice implementing it was becoming a much bulkier load, right? So that was the core concept behind Istio, that, hey, let's take these common functionalities, create a service mesh layer, right? And which provides those common functionalities or common services versus, having every microservice implemented. Again, a project which has become hugely popular, right? Initially founded by Google, IBM, and Lyft. IBM is the second largest contributor here as well. And if you are using, IBM Cloud ecosystem and IKS, right, you will be fairly well versed with all the offerings we have around, how to get Istio on the IKS clusters you are spawning, right, the managed Istio service there. So now let's take these together and apply it in the context of KF serving, right? So the first point was, we definitely wanted, the concepts of default and a canary, right, which are the core constructs in Knative, right? But one of the things which we did observe was, as opposed to the application world, right, machine learning world, given the experimental nature, you will be changing revisions of the models you are deploying. And as you are changing revisions, even if they are not ready to roll out, you will be iterating over multiple of these revisions before you finalize your revision for a rollout, for example, for Canary or even for default, right? So changing revision every time leads to a new configuration that was Knative construct, which didn't align well with the machine learning side of the house, right? So we took a diversion from there where we now allow that, you can iterate and create multiple revisions before you decide what is your canary or what is your default. And then, leveraging the capabilities around splitting traffic, right, which come as part of the Istio ingress load balancing capabilities, right? So that allows us to then, okay, you're rolling out a canary, you have finalized your revision, and then you now want to, test out and split traffic and ensure that it's performing well before you start ramping up that load. So different kind of model servers supported, that was given the diverse world we are operating in and different ecosystems, right? Microsoft, for example, is heavily standardizing on ONNX runtime, right? So they contributed the ONNX runtime support there. IBM is contributing heavily there as well, and the project is in LFAI. Google, by its virtue, is doing a lot on TF serving, right? So TF serving runtime. Now, NVIDIA has been focused, very heavily on optimizing these models in terms of the GPU consumption, right? And in a lot of cases, if you're using NVIDIA Triton's inference server, you probably, for the same model, you're getting much better performance, out of the GPU, as opposed to, for example, just using TF serving natively, right? So NVIDIA's Triton inference server is integrated there as well. And then we built, custom servers where we didn't have, right? So we didn't have scikit-learn, XGBoost, PyTorch. So, that was built as part of the cave serving project and provided there. Now for PyTorch, recently, I believe around a month ago, AWS has came out and contributed Torch Serve to the PyTorch community. And now they're also working on contributing Torch Serve integrated in KF serving umbrella, right? The components focus initially was around the predictor, explainer, and transformer. And somebody had a question previously, what does a transformer mean? So this is essentially what a transformer does in our context. I have a slide later, right? Which essentially allows you to plug in your pre-processor and post-processor around your predictor, right? Then we have AWS, GCS, Azure Blob, PVC, all different kinds of backend storage supported based on the storage needs you have. So more on the transformer, right? So this is something, which is in your inference routing path, and you decide, whether you want to use it or not, you want to enable it, right? And the goal of the transformer is, if you have a custom preprocessor or a post-processor along with your model, which needs to go with it, right? So one of the examples which I typically use is that, your model is just using tensors in and giving tensors out, right? But you typically, from your end users, when they are asking your model to explain an image, for example, they're providing an image format file, and then they're getting text as an output. Now, where do those functionalities go? General practice, I would say, and probably bad practice in the industry, a lot of people essentially, bundle up that pre-processor and post-processor with their model serving code. Now, the problem with that kind of approach is, it's tightly coupled with your model prediction, which is, working on the training data and getting produced. B, you are, technically also leveraging the same expensive resource, which is more suited for the heavy duty task of prediction, right? For example, the GPU, but your pre-processor and post-processor, which are doing, less compute resource intensive tasks, they're also, consuming the same GPU. Right. So in general, I think the bad practice in the industry, and that is one of the things which we want you to decouple these and bring it pluggable. So, you have the capability to launch your pre-processors and post-processors on CPUs and let the prediction, right, which is where the bulk of the heavy lifting happens, be running on those expensive GPU machines. Now, when you deploy it, you get a view like this, which is essentially, you have the Istio ecosystem, which is around that, and then the Knative serving, right, which brings activator, autoscaler. And I have a slide, explaining those components a bit more as well. But then, for example, if you've deployed a predictor and an explainer, right, each of them get their own pods, which their own containers, right? There is also a storage initializer, which is responsible for, downloading and bringing and caching your models, closer to where the pods are. Now, another effort which I mentioned was, the data plane unification. So in the first iteration, we aligned around KF serving v1 data protocol, which is, aligned around the TF serving compatible HTTP API. And the goal was, okay, listing which models are deployed, are the models ready, what is the endpoint to predict, what is the endpoint to explain. That's all aligned with TF serving in the v1. In the v2 protocol, we worked heavily with NVIDIA. NVIDIA essentially, drove the majority of that initiative, where we standardized and agreed on a data plane v2 protocol. And by virtue of NVIDIA, driving majority of it, they also were the first ones to get it implemented as part of the NVIDIA Triton Infinite Server. We are now implementing that across PyTorch, Scikit-learn, XGBoost, in both Seddon as well as KF serving, right? So you have the same protocol running around NVIDIA Triton as well as PyTorch as Scikit-learn, XGBoost implementations. We have, on paper commitments from the Onyx team to actually comply with that protocol as well. And then, the next in line would be the TF serving, where we need to have that discussion. So, okay, now that you have these capabilities, how do you deploy your models, right? So as I mentioned, Kubeflow in general is built around the principles of Kubernetes custom resource definitions. So KF serving is around that principle, and that by virtue of it, you have YAMLs and you can use kubectl, right? So simply in this case, right, if you look, you're deploying a TensorFlow or a Scikit-learn or a PyTorch, but with 7 to 8 lines of YAML here, but consistent. Point to your model, deploy this, and use kubectl apply. If you want, more advanced capabilities now around canary and pin rollouts, then you start adding more to that bits, right? So in this case, this is a canary version of my model, and the traffic I want to send to my canary is 10. You can specify as part of that, or I want to pin my default model, right, and change the canary traffic bus into 0. The underlying backend engines, right? So TensorFlow serving is supported. It's very, very stable. Google has been using it for quite many years now. It's written in C++, supports both REST and gRPC, right? And by coming as default option, one of the options in KF serving, right, it allows you to now spin off this in an auto-scalable fashion, right? And it shows that it's working and correctly configured with underlying GPUs and CPUs on your infrastructure. Now, this is typically a BERT model, right? Which is, if you're deploying using KF serving, you can point to your predictor. Your predictor can also, specify how many limits you want to push on the GPU side. And the transformer, as I mentioned, right, you can point to your transformer, but you don't specify that you need GPUs there. Now, this will remain consistent across multiple of these runtimes, right? So NVIDIA Triton Infinite Server, right, it also provides a few more capabilities around that, right? Model repository versioning, dynamic batching. So if you are using that, essentially the same exact mechanism, but you point to, the TensorRT, you add that particular tag in your predictor, and then it is, the runtime version you are trying to use, and it will point to that. PyTorch model server is something which we implemented. Tommy and I contributed the first version of it. Bloomberg extended it to add GPU support, and Bloomberg is currently using it internally extensively, right? And our goal is you can use this, you can use Onyx runtime, which comes as part of the default as well, right? To convert your models to Onyx and then serve it using PyTorch. And the next in line is, the Torch server, right? Which AWS is working on contributing towards KF serving. If you're not in the Onyx ecosystem, that's a project where IBM is invested. There is a lot of work happening across our mainframe and Z subsystems, because the place where Onyx typically shines is, optimizing one model serving protocol and framework, right, for your hardware. So the mainframe teams are taking advantage of it and optimizing it. So you can start from any of the different model server frameworks like TensorFlow, PyTorch, scikit-learn, right, train. But then once you have trained, you can convert it to Onyx format and then launch it on Onyx runtime, right? Um, Microsoft is the one, right, which is doing, or in fact, consuming Onyx heavily internally, right? So very well suited for folks who want to standardize around one single protocol. Now, it comes with a caveat that not every operator in the TensorFlow world or PyTorch world, you might have supported, right? So typically, IBM leads the TensorFlow operator, right, for the most part, and our community is heavily contributing to it. But you would probably get most of your TensorFlow models converted to Onyx, but there might be few, right, which you are not able to convert because that operator is not supported in Onyx. Again, similar mechanisms, right? You essentially specify similar YAML. This is my predictor. This is my transformer, consistent across the board, right? So from an end user perspective, there is no change how they are deploying, where they're deploying, right? As long as the YAMLs, the formats, they remain consistent. Now, in the context of Knative, one of the things which I also talked about was the activator and the autoscaler, right? See, activator is a component, right, which is responsible for buffering the request when you start getting, request to actually start scaling up from 0, right? And then the autoscaler is the one, right, which is then working behind the scenes, looking at the metrics of the activator as well as the kube-proxy on the model serving side in KF serving, and based on that, right, it's making a decision whether to scale up or scale down. Now, by virtue of using these combinations, right, you have much tighter control on deployed models. You are able to roll outs, you are able to split traffic, and you are able to auto scale based on request-based metrics or your request queue, instead of auto scaling based on GPUs and CPUs. The problem with auto scaling based on GPUs and CPUs is that there is not a consistent mechanism, right, to know the utilization at that particular level, and you will get bursty traffic at best, right? So with using a request based or queue based auto scaling is more aligned with the direct business goal, which is if there are more users, we have more infrastructure. Simple as that. Now, with all these capabilities, for data scientists, right, the things have been made very easy. But that's not, the only way. If you don't want to see a YAML at all, right, if you're a data scientist and you don't want to see a YAML at all, there is a KF serving Python SDK, right, and we are going to demo it a bit later as well, which you can use to just work using the native Python mechanism. Currently, this is deployed at scale across Bloomberg, CoreWeave, Gozek. The whole of Bloomberg's infrastructure is currently serving models in production using KF serving, and they're working on as you imagine Bloomberg's use case, the amount of data set they collect and produce, and building models out of it, right? That BERT is probably the most heavy hitter there, but they're successfully running this in production. CoreWeave is hosting. If you play one of these games called AI Dungeon, right, which is thousands and thousands of users, right? That whole game is running on top of KF serving as well. Okay, so I think we sort of summarize a lot of the benefits, right? Queue-based auto scaling, different kinds of protocols, permitted, selectively deciding what can be run on GPUs, what should be run on CPUs, right? But there are other problems to be solved, right? You have served your model, you have good control over rolling it out in production, good control over figuring out what is going where on GPUs and CPUs, etc. But you need to be able to have more quality metrics around that deployed model, right? Things like, are there drifts? Are there outliers, right? Can your model explain its predictions? Is your model vulnerable to adversarial attacks? Now that was, one of the primary focus we wanted to make sure that, is being handled in KF serving, right, from the outset as well, right? So to enable some of these advanced capabilities, we needed something what we call, payload logging, right? So something like explanation, like if you're just looking at a transaction-based explanation where I send a prediction request and there is a prediction response, that can work, for the most part, out of the box. You don't need a payload logging. But, there are different kinds of explanations, right? So there are global explanations where you need to analyze the model explanations over a period of time. Sometimes, there are black box models which you need to collect and train a surrogate model to generate those explanations. And to do those kind of things, you need historical analysis of the incoming prediction request and response. So that's where, the logger came into picture. It essentially, collects the request and responses from the models, and then it's implemented using the native Cloud Events protocol. And by virtue of it, right, you can configure it to send the collected payload, for example, to a Kafka broker or to a relational database or to, a document database, right, wherever you want to store it as part of that ecosystem. Now, once it is there, then, you can have it configured to then, trigger that there are outliers or there are, adversarial vulnerable predictions, there is concept drift, all that can be enabled using that. So as I mentioned, this is implemented using the Cloud Events protocol. Now, Cloud Events is an effort in CNCF. Doug Davis from IBM has been, heavily involved in it in terms of advancing it. And this is a standardized way to define your events. That's what we are using for KF serving. And you can add it to any inference service endpoint, right? You can collect request responses from predictors, explainers, transformers, right? And you can log all of them and using the Cloud Events protocol. Now, typically going back to the YAML, right? In this case, right, then you will point to where the logger is, right? Where you have it configured, and then based on that, right, it will start collecting and sending your payload request and responses to that particular logger. Excuse me, right? And then, as I mentioned, you can have different places where the logger can be configured to send. But given that it's aligned with the Cloud Events protocol, you can have it configured to send it the same payload log to different kind of mechanisms, whether it's a Knative broker or you have a Kafka bridge where you want to send it. Both can be enabled, or multiple others, right, which are supported. So now once you have that infrastructure in place, right, where you can now provide more of these advanced capabilities, so you're able to connect payload logs, you're able to, store them and serialize them in some format which you can do analysis on. Then you can start providing these more advanced capabilities, right? So explainer. Now you can use the default explainer, right, which is there in KF serving, but you can bring your own explainers and point to and plug in that particular explainer here as well. Again, that requires an extension to your YAML, and you say, okay, I want explainability as part of it. What type of algorithm I wanted to use, anchor text, anchor tabular, and you can, enable that. Now, the current implementation default, which is out there, comes from Selden's team, right? And they have state-of-the-art implementations around anchors, counterfactuals, contrastive explanations, which are available. We have an internal prototype running where we have integrated AI Explainability 360. Andrew from our team has done quite a good job on getting that done, right? So this is going to be, moving it out in open source as well, right? So, and this is what technically, also aligns with the core of what's an OpenScale, if you use it from that perspective. And a lot of, algorithms are available. So if you're interested in learning about it, right, you can go to that particular link. And AI Explainability 360, takes a much bigger approach at explainability, right? So not only looking at, model predictions within a localized context, but also, model predictions over a period of time, looking at black box models, but also, providing explanations around your data set, right, on samples and features. How will you get that integrated, right? So we will be moving it out soon, and typically the same extension mechanism, right? You provide that, okay, I need to run explanation, and these are the characteristics, and if you want to put resource limits, you can put resource limits on your explainer as well. So then there are more, advanced capabilities which I talked about, right? Outlier detection, adversarial detection, concept drift. Now, typically, if you look at outliers, you have different kinds of them. For example, if you look at speech data, a lot of the pauses, a lot of the ums and ahs, right? They're typically outliers which don't do anything meaningful in the speech data, but they definitely need to be identified and sort of, something which we probably shouldn't be too concerned about, right? So those are, more contextual outliers within the context, like say, as I mentioned, the speech data and a lot of the pauses you are taking, etc. But also collective outliers, right? So typically, a lot of times it happens when you deploy models in production, you start seeing some, the emergence of a new phenomena, right? Where your request response is essentially going in areas you didn't identify before, but there is a cluster forming there, which tells you, okay, for that particular cluster, the model is behaving in a totally new, different way, right? So all these capabilities, which you want to detect as part of the outlier detection. Adversarial detection is more focused around identifying vulnerabilities in your model predictions, right? So a lot of the cases which are happening are around, where you can insert adversarial noise in your inputs. More often than not, those adversarial noises are undetectable to the human eye, right? But when you actually, feed it to the model to give a prediction, it can make a totally different result. In this case, right, if you see there was an adversarial noise inserted in the image of a pig, and then the model output, comes back and talks about an airliner, right? So very important field. It's happening a lot in the bank fraudulent cases where, I can make a 1 look like a 7 without, having it visible to the human eye, but strong enough for a bank to give me $700,000 when the person who's signed was $100,000, right? So a lot of cases, emerging like that for adversarial detection. So, and then the concept of concept drift, right, which is essentially the distribution you're getting in production data is not essentially mirroring what you had in your training data, right? So to enable all these capabilities, right, there are quite a bit of samples in the Chaos Serving repository, how you can leverage these capabilities, but you definitely need, payload logging to be enabled to be able to have, more advanced analysis around outlier detections, adversarial detection, etc. Right, we have quite a bit of samples there into Chaos Serving repository. Obviously, we won't have time today to go through each and every sample. We'll try to show, a few of the things here. But these are the capabilities which are available. Now, if you are following IBM, right, you are aware of a project which we have in this space called Adversarial Robustness 360, which essentially gives you a tool to craft attacks on your models and detect vulnerability. If vulnerability is found, it also gives you tools to implement defense algorithms, right? And assign metrics. So very popular tool as part of our Trusted AI umbrella. It has been, donated to Linux Foundation AI and open governance. And this is something, again, we are working on integrating with Chaos Serving. We have an initial prototype, so we will be moving this integration in open source soon as well, where you have adversarial robustness toolbox providing these capabilities for Chaos Serving, right? It works across the machine learning. What you see here is a subset, right? So you need to update this diagram, but essentially, ART goes across machine learning models like scikit-learn, XGBoost, in addition to deep learning models, or CatBoost even, for example, and very extensive rich set of algorithms around that. Plus, it works on all kinds of data, image, text. Okay, so with that, Tommy, do you want to go through the first demo? Are you here? Is your laptop good? Or otherwise, I can go through
Yeah, I
this.
could show the demo.
Okay, cool. Thanks.
So for today's demo, you can also find it under the Kubeflow Dojo. There will be a demo link. You can follow along. And this demo is created for the dojo. So first, you could get the notebook, download the notebook, and then upload to your Jupyter server. And then once you have the Jupyter server running, you should be able to open Jupyter notebook like this. And first, you will need to update the URL to your own Kubeflow endpoint, so you could use it to run on your own cluster. So let's go ahead and do that. The first example we're going to go over is using the YAML files and using kubectl to just apply it directly on Kubernetes. To define it is pretty simple. So you have like the define the kinds for the Kubernetes. So it's inference service and the API versions. So it knows which Kubernetes APIs to talk to. And then we call scikit-learn iris models. And the model source is going to be stored in the GCS bucket. And once we have that, we just write that file in and then apply it. Once you apply, you should be able to see there's a pod initiated, and you can see it will say not ready at first. After it takes a few seconds, it should have all the pods finished running and be ready and show you the endpoint. So let's go ahead and see. So it will take a little bit more time. So as you can see, once it's ready, with all the containers running, it will show you it's being ready and have a URL that you could ping to. And since this URL is not technically it's not public, so we have to post it using the Istio Ingress Gateway, which is shared by the same reverse proxy as Kubeflow. That's why I have to define the Kubeflow URL beforehand and use it over here, and then put the host name as part of the curl request. And once you have that, then we could go ahead and launch a curl request. You can see the prediction is just return 1 and 1. And you have your curl payload over here as well. And you can see it returns 200 success OK. That is one of the example using like just pure Kubernetes commands. So let's go ahead and clean up these examples and go and try out with a different client. So in the second examples, we're going to show you how to use the Python SDK to do everything using pure Python. So to do that, we have to install a list of SDK for, let's say, building the models and running the KEF serving clients. So let's go ahead and run this and install behind the scenes. And once we have installed, we have to define a inference functions. So in Python, we'll use the request library to do our curl request. And then we will define our payload as an image. And for this example, we're going to use a TF-flower dataset where it has 5 different classes for the flower. You want to know more about the TF-flower dataset, you could go to the TensorFlow link. It will have more details on like which category the flower is in. And then once we have the library installed and define the inference function, then we could start declare the clients for KEF serving. So this will declare both the Kubernetes clients and the KEF serving clients. And then define a namespace that you want to use. So in this case, we just use our default namespace in this notebook. And then here is the same thing that you see in the kubectl, but with the Python format and executed with a Python client. So you can see you also have the same thing with the predictors, but it's defined with Python predictor spec. And then you also have the source that's pointing to a Google Cloud buckets for the models. And at the end, you can also specify like Kubernetes specific requirements, like how many CPU you want to run for this model and how many memory you want to assign. And at the end, you just define the actual inference service using the spec you have defined above and wrap them together with the names and namespace. And once you have everything, then now we could declare the KEP serving clients and actually create this inference service you have defined above. And this you can see the Kubernetes return the command saying the create is successful. And then you could also do a get function to actually watch the status of this inference service model. So first it also show you it's false, but since we will keep watching, so every time it changes the stage, it will show you what he have changed and show you when this is become ready. So while we are waiting, we will go over and show what we'll be using for the inferencing. So we're using this dandelion picture of a flower for the inferencing. And now we see the models being deployed and the URLs over here. Then we could go ahead and take the Kubeflow URL as our input and take the TF request that we have defined in the first cell. And because we call our model flower sample, so we use that as well and call the inference functions. So this will create a request with this image encoded into base64. So once we click on it, it will send a request and wait for the response. And once the response is back, it will print out the result of which class is this picture in. So as we can see, it has very high confidence score for the first class, which is the dandelion. So that's what we expected. And the rest of the classes have very low confidence score, as you can see over here. And that is using the SDK. So let's clean up the example over here. The next example we're going to show is how we could wrap all these together and put it into a Kubeflow pipelines. So to do it on a Kubeflow pipeline, we would need to use the KFP SDK. So first we declare the KFP client for Kubeflow pipelines. And in this example, we're going to deploy a canary model, which means we have two versions of the model. One is the default, where most of the traffic is going to. And then there's another version called Canary, where it only split 10% of the traffic. And we will see how well it do. And if it's doing good, then we can also promote the Canary back to default as a new version. So to do that, we first define the pipelines. So because we already have something already predefined in the Kubeflow community, we could just pull it directly from the community GitHub repo. And then once we have the KEP serving ops, then we could define a set of parameters that we want to put in. So the action we want to do in this pipeline is just to apply this model to the Kubernetes cluster. And the model endpoint is defined over here. We have two different versions, so the endpoint will be different. And we're only splitting 10% of the traffic to the Canary models over here. And the framework we're going to use is TensorFlow. And we'll deploy on this notebook namespace, which is anonymous. And then once we map those parameters to the operation, to the container ops, then we could define the compiler to compile and then run the pipeline on this notebook. And once we run the pipelines, then it will show you like a run link, which it actually trigger pipeline run on the Kubernetes cluster. So you can click on the pipeline run over here. it would be start running. Then you can click on the logs. It will show you pretty similar as the log you see in the Python client, because it technically wrap the Python clients behind the scene. So you see the same TF-Flower models is being deployed, but with the canary deployment. So it would probably take 2 to 3 minutes. So we could wait a little bit. And once it's ready, then we will show you, in terms of the canary version, it will show you how many traffic is for the default and how many traffic is for the canary. So you can see like 90% traffic going to the default, 10% going to the canary, and you have the URL that you could ping to. So right now, let's go ahead and do a smoke test with the inference. So we use the same function for predictions. And you can see it's the same result. Dandelions is our picture for the predictions. And now let's see how this traffic is passing over to these two different models. So we'll create a while loops and do the inference. And we call the inference request over and over. So right now it's keep calling the same request over and over and sending traffic to both of the models. And to visualize it, one of the good tools to use is the Istio Kiali consoles. So when you deploy Kubeflow, you will see Kiali is being part of the monitor tool inside the Istio system namespace. And if you expose that into a node port and access it over here, you should be able to see or monitor the traffic of all the services you have under this particular namespace. So right now we're under the anonymous namespace where our notebook is running. So you can see our notebook is receiving traffic from the Istio Ingress Gateway. And then also we are pinging traffic to the two services we have just created. One is the default models, which it gets 90% of the traffic in HTTP. And then we also have the canary over here, getting 10% of the traffic from HTTP as well. Because Kiali, I always show you like all the services, so you also see like some of the services we have deployed before, and it will still have some history until like a few hours later and clean it up. And that is the end of the canary demo. Up to this point, you could try out on your cluster as well. And then lastly, we could also promote the canary models to default. So once you satisfy with your result of your canary models, then you could call this promote functions. It basically promote your canary version into default and route 100% of the traffic back to the default. So once you promote it, it will redeploy the model with the correct version. So it will move the canary version back to default versions. And then it will probably take another 2 minutes to restart the pod. And once you have that, you should be able to see the TF-Flower is ready and have 100% of the default traffic. And that is the end of the canary examples. From the step 4 and beyond, these are like the very advanced example where it will require a lot of memory and CPUs. So we will just go over how it looks like. And if you want to try it out, you probably need a bigger Kubernetes cluster than what we have for the Dojo. So let's go over like the concept of transformer. So for transformer, we have like endpoints that passing to a transformer container first to do pre-processing and post-processing. And after the processing is done, then it will call the predict request inside the transformer container and get those results in, and then do the post-processing and return back to the user. And to define a transformer is pretty simple. So in addition to the predictor you have defined in your inference service, You just add the section for the transformer. All the spec is pretty much the same as the predictor, but except you're not using deep learning framework. Instead, you're using a custom container to do your own pre-processing and post-processing. And you could limit your resource as well, similar to other examples. So once you deploy it, you should be able to see there's like two different part is being created. One is for the predictor, which is actually processing like the model request. Another one is a transformer where it's going to do the pre-processing and post-processing inside this part. And then you will have to wait both of the parts to begin running before it says the whole model endpoint is ready. So we could wait for a little bit, and let's go ahead and explain a little bit on the model. So the model we're going to use in this case is the CIFAR 10 dataset. It just set up images with 32 times 32 pixels with 3 different color channel. And for this prediction, we're going to use the cat image for our payload. And we will define the payload embedded in base64 format as well. So let's see. So once I think we're still waiting for the model to finish, but I could explain the payload. So once the payload is encoded into base64, because this model is not encoded for images, so we have the transformer to actually process the image and convert it into like 32 times 32 times 3 matrices. So let's see. Once this is start running, yes, we get the transformer endpoint. And then you can see the prediction is the 4 categories cat, and then we'll go ahead also like trigger the traffic, so you could also see how this is being executed on the Kiali dashboard. And for this workload, it's better to use the workload graph, so you know how each services is triggered. So over here, you can see a lot of the traffic is going to the transformer, and transformer like process the request. And then finally, it will send it to the activator where where Knative is queue up all the requests, and then later on, those requests is also being sent to the predictor and actually predict the result and return back to the transformer and then return back to the user as predictions. So that is the demo for the transformer. And lastly, we also like talk about the X360 library. So we are going to show you how you could embed your like custom explainer as part of the deployment. So for explainer is similar to the transformer. You just add the extra sections with your custom container to do the explanation. And any explanation that require model request, you could just call the predictor that you have defined above. So in this example, we just use a simple MNIST models with doing the handwritten digit data sets. And let's go ahead and apply it and wait for it. And while we're waiting, let's go ahead and explain the workflow. So first, the whole explainer is located over here, and it's listening requests from the Istio gateway. And the Istio gateway is also taking any requests from the client. So once the client is calling the explainer, it will first send a request to the Istio gateway. It route based on like the host name. Once the explainer will receive the request, you will need to make multiple sample predictions in order to know like how the models behave. So it will create a bunch of sample predictions, and those predictions is routed into a local gateway for Istio, which is calling the predictor behind the scene. And the predictor will give them a bunch of sample predictions. And the explainer will, based on those prediction results, and conduct an explanation on why this model is predicted for this particular class. So once we have everything's running, you should be able to see an endpoint. And here is like a long functions for actually getting the MNIST data sets and then send the request. And at the end, once we get the result, we kind of plot those results into like different images. So you could see like how the result is displayed in terms of the plot. So we go ahead and run it. So first we can see our payload is an image of 2. This is our original image. And then once we receive the results, the result says it's 2. And then underneath we have the explanation, and we kind of plot it out and explain why we predicted as number 2. So you can see for number 2, most of the feature is being positive. So that's why it says for number 2 over here. And you look at other classes, let's say for 8 and 1 and 4, they also have a large amount of features being positive. So it's more likely if it's not 2, then the next possible outcome class, it could be 8, 4, and 1. And you could see for 9, 5, 3, 6, it's probably not going to be predicted because like there's no possible features that is used with these classes. And also like at the end we'll show you like how to do a performance test. But I think we are sort of run out of time. But basically the idea is like when you have something that's have heavy payload, you could set the auto scaling to 10. So once you have a lot of requests coming in, it will auto scale it up to 10 pods to receive all the traffics you have and process it automatically using the knative scale functions. So that's the end of the demo. Thank you very much.
Thanks, Tommy. I think we are right at the point. So I believe we'll probably take questions. There is another demo we have, right, which I showed yesterday in the main end-to-end talk, right? So if there is like enough new audience, right, we can show that. Otherwise, we can take some questions. So okay, so the one thing is default canary is great when both are compatible with the client. If you get a new version of a model that is now incompatible with client, I assume this is basically treated as a new. I probably need to understand more context around that, Jeffrey, right? But one of the examples, right, which Tommy was showing was, right, if you see in this context, right, the URI which you see, right, these are 2 versions of the model, right? One is at this location, the second one is called, flowers-2. Right now, when you have deployed the default, right, this is not what you are getting as an endpoint, right, to handle that model. You get a standardized endpoint to make predictions, and you have deployed canary, which is a different endpoint, right? But then if you are happy with the canary, you can promote, right? So you can say that, okay, promote this canary to be the primary, and by that point, if you are able to promote, then you end up with the same URL, right, for your prediction endpoints. So essentially, even though it was a new version of the model, but as long as you specified it as a canary version, which needs to be rolled out and make the default eventually, then by that point, when it is deployed, the endpoint remains consistent. Now you can entirely choose that, a new version of the model becomes a new deployment, and I don't want to classify it as as a canary, right? So in that case, there will be a different endpoint, if that answers your question, Jeffrey. Okay. Cool. The second question is, how do we get to Kiali console, right? So Kiali by default is not available as part of the Kube serving deployment. I don't think, or Kubeflow deployment, right? This is a monitoring dashboard, which we deploy after the fact. You were going to say
actually, it is part of the Kubeflow deployment that we have. So I think you look at the Istio system namespace, you should be able to see the Kiali, but by default, it's not exposed to the public. So you have to choose to expose it either via no port or load balancer, then you could access from the public web.
So that's great, Tommy. So do we add it as part of the our KevDev, IBM KevDev, or is it something which the...
I mean, there's an extra command you have to run to expose to the public because we don't want to keep too many visibility for those dashboards.
I think the question I'm asking is like, if somebody picks up Kubeflow from the community, right, will they get Kiali?
I think at this point, you use the latest chart, you will have it.
Okay, so you're saying that the latest Kubeflow installation by default
right.
was...
You will have it by default, yeah.
Cool. Okay. Yeah, Scott, so maybe, you can ping Tommy and he can get you going on that side. Fork, yeah, I think, this was not intended to be hands-on, but if you do want to try it, like just work with Wei Shang, right, on maybe the Kubeflow Slack channel, the Dojo Slack channel, right, and you can probably figure it out, if something is not configured right in your environment.
Also, Animesh, just to add, I think the Istio installation comes with Kiali. So I think if you're just installing Istio part of Kubeflow, that comes with this Kiali built in. That's why you're getting Kiali. Kiali was like made a standard installation for Istio.
Yes, I think for Kubeflow, we all have like custom templates for like Istio Knative. We're not using the one directly from community. We have some custom config.
Good. So any other questions? Besides Kube serving, I think hopefully, you are all excited about this project as much as I am. Or, in general, the community is excited about, right? And just in the context, there is also a strong interest from Watson side, right, to, I would say, align a bit more around Kube serving, right? So we're working through those. There are no concrete plans, but we definitely, even from a product perspective, there is strong interest in terms of, looking at that angle. Okay.
There are more questions again.
I think what is happening is, people are, and maybe, this is not supposed to be hands-on and people are trying to do hands-on. So probably not that tested too much, but I think, the best person would be, probably Wei Shang to post the talk, right, and see,
right. But there is a question about how many days the clusters will be available. Will they disappear today?
By tomorrow. I believe it's probably a day after the workshop, right, when they're supposed to decommission them.
So now it's the lunch break?
Yes, so we are at the top of the hour, right? So this is a lunch break. After that, wrapping up the day.
Great. So a break for an hour now.
Yeah, thanks. And meanwhile, if Wei Shang and Tommy, if you can maybe, just spend 5 minutes and trying to see, what might be wrong with the Kube serving deployment in case of fork, and just help him out on that side. Other than that, we do a breakout here. Let's go for lunch. Thanks, guys.